Hello, Science 10s. Welcome back for another chemistry lesson. What we're doing today is part of Unit D. So I don't know if you'll remember. I mentioned this in class a while ago, but Science 10 is sliced up into 4 units. So A is chemistry, B is physics, C is biology, and then Unit D is kind of the environment. So what I did is I split Unit D up and I kind of put little bits into the other units just to make it go a little bit quicker. Um, so this is not actually in your Unit A. If you want to read along in your textbook, you would flip to Unit D, Section 2.3. Okay, so I like to put this into the chemistry because it deals with moles, it deals with reactions, and I personally think it belongs in this particular section. Okay, so if you haven't looked at the lecture on the mole yet, you might want to do that because today we continue on to use that measurement, the mole, in some more equations. Okay, so stop it here, go back, take a look at the mole if you haven't done that yet. All right, so we are going to move on into section D, Unit D, section 2.3. Okay, so it's still a continuation in your note package. I just put some of that Unit D information into Unit A. So I briefly touched on this in class one day when we were talking about water. Water is an incredibly unique molecule on this planet. It has some properties that no other molecule has. Um, you might have heard that our bodies are, whatever, 65% water or 80% water, or whatever the number you might have heard. And of course, it depends on the tissue. For example, blood is 90% water, right? Whereas bone has very little water. Generally, the tissues where lots of reactions occur have lots of water, and that's because things can dissolve in water, especially ionic compounds, so salts and that sort of thing. Water is a very good solvent of polar molecules, so molecules that have charges like ionic compounds. Okay, water, and the reason for that is water itself is polar, and I'll talk more about the structure of water here in a second. Something incredibly unique about water is that the solid form of water, ice, of course, and snow, is actually less dense than the liquid. So let's think about that for a second. You guys were taught, the particle theory of matter, that in a gas, the molecules of a gas, particles of a gas, they move quickly, relative to the liquid and solid. Okay, they move quickly, they bump into each other a lot, and they're far apart, right? So they have a very low density in a gas. In a liquid, they're closer together, yet they still move freely. They can take the shape of a container, right? They do bounce into each other, but less than a gas. And then finally, a solid. You guys learned in junior high that solids, their particles are very tightly packed. Solids are very dense compared to liquids and gases, and the particles don't move around very much. Well, water is the only substance that I know of where the solid form is actually less dense than the liquid form. Okay, think about that for a second. So the particles of water in ice, okay, if you went and got an ice cube from your freezer, those particles have more space between them than the particles in a glass of liquid water. Okay, this is why you can put ice cubes in your glass of water and they float on top of the water. We take this for granted. This doesn't happen with anything else. If you melted down some iron and you took a solid chunk of iron and put it on top of that iron, that liquid iron, the solid would drop to the bottom because it's more dense than the liquid, right? Everything is like that, except for water. And that's really important because ice floats on top of water. And if you're an aquatic organism, you can live over the winter underneath the ice that's floating on top of a lake or river. Okay, if this wasn't the case, ice would form on top, it would fall to the bottom. More ice would form on top of a lake, fall to the bottom, and eventually the entire lake would be ice. And of course, nothing can live in solid ice, right? So we wouldn't have the life we do in aquatic environments, especially in northern latitudes. But what happens is ice forms It floats on top, like we're seeing in this picture, and eventually it kind of forms a shell, and that insulates the bottom water, and it stays above freezing for the entire winter, and things can live underneath in that liquid water. So, incredible property that allows life to live through the winter. Then we have cohesion and adhesion. Now, in your note package, I want you to make a note. There's a typo in your note package. Um, in your note package, surface tension is where behind adhesion. Okay, surface tension is actually the result of cohesion. So sorry for the confusion. Just cross that out over here and put surface tension up to cohesion. Now, what's the difference? Okay, co means kind of together, right? So cohesion is the property of water molecules where they like each other. Okay, because they are polar, they tend to stick to each other. Okay, so what this means is there's forces between water molecules, and that creates almost like a skin on the surface of water. Okay, so for example, this thing right here is called a water strider, and you can see that it's sitting on top of the water, and it's not floating on the water. Okay, it's actually sitting on the water, and you can see that its little legs here are denting the water. Okay, almost like if you were to, if your friends were to stretch out a big blanket and you were to lay on top of it, right? You're not floating on the blanket, you're actually being held up by the blanket. And that's kind of what's happening with this bug. And that's what happens with many things. Now, floating is completely different. I believe it was Archimedes who talked about, you know, uh, displacement and all that kind of stuff. Okay, this like I said, this bug is not floating; it's sitting on the surface of the water. Okay, now adhesion means that water molecules will stick to other things. Okay, um, like the side of a glass or the side of your sink. Okay, so they will. They will be attracted to other surfaces. Okay, so water molecules are attracted to each other, right? And adhesion, water molecules are attracted to other substances. So what we're going to concentrate on in this section is something known as specific heat capacity. Okay, so water also, because water molecules are attracted to each other. So when we draw a water molecule out, we draw it out kind of like this. There's a slightly negative charge at the top. There's a slightly positive charge at the bottom. That's what this Greek symbol means here, slightly. Okay, so the slightly negative charge at the top near the oxygen means that the electrons spend a little more time around oxygen, a little less time around hydrogen, and that gives it a charge. Okay, so because we have opposite charges on opposite sides of the molecule, we call this polar. Now, because each water molecule has its own charge, this water molecule is going to have a negative charge and a positive charge. This water molecule is going to have a negative charge and a positive charge. Okay, they set themselves up in what's known as a matrix, and the positive ends of one water molecule are attracted to the negative ends of the other water molecule, and this is on the last slide we called this cohesion. Okay, so these bonds between water or between one water and another water, um, they're not sharing electrons or anything like that. These are known as hydrogen bonds. Okay, and hydrogen bonds cause cohesion of the water molecules to each other. Now, because there's this little bit of an attraction here, it takes energy to break apart these water molecules from each other. Okay, so specific heat capacity refers to the ability of any substance to absorb energy. Okay, now because water has these hydrogen bonds between water molecules, okay, there's a little bit of an attraction there. It takes a lot of energy to break apart these hydrogen bonds, and because of that, water can absorb quite a bit of energy. Okay, so water would have what's known as a high specific heat capacity. It's some of the highest around on planet Earth. Okay, which means that you can put a lot of energy into water without having the water molecules separate and change state or change temperature. Okay, and that has to do with the hydrogen bonds between water molecules. Now, this accounts for a phenomenon that happens with temperatures around coastal areas. Okay, so for example, Vancouver, BC. I don't know if anybody's ever been there. I haven't been there myself. I hear it's beautiful, but Vancouver is right on the ocean. It's on the Pacific Ocean. Okay, and the thing that makes Vancouver really, really attractive for people to live, right? Like houses there cost, double or triple what they do in Edmonton. There's lots of people there, and the reason why so many people are attracted there is because they don't have huge jumps in temperature. So in January, okay, you might get below zero on evenings. Now, of course, once in a while, they'll get snow, but very rarely. So we might have an average temperature, low temperature in January of 0 degrees Celsius. Okay. And in July and August, the hottest month, we might have a high temperature of around 20 degrees Celsius. Okay. Again, does it get to 30 above in Vancouver? Yeah, very rarely though. So the temperature fluctuation over the year from the lowest low to the highest high averages we're talking is only a 20-degree difference. Okay. So in Vancouver, averages only about a 20-degree difference between the lowest low, average low of 0 degrees, and the average high of 20 degrees. Okay, now let's take a look at another city that's on the same latitude as Vancouver, but not on the, and this is Lethbridge. Now, Lethbridge is pretty far south. Again, I don't know how many of you guys have ever been to Lethbridge. Nice little town. It's on the prairies, though. There's a river that runs through it, but there's no large body of water anywhere close to it. And what we find is that the average low and the coldest month is around minus 15. Again, that's average. It often gets to minus 30, minus 40 down there in the wintertime, right? Um, and the highest highs, as far as average temperature goes, is around 25 degrees, right? So this is a disparity of about 40-degree difference, okay, between the highest high and the lowest low. So that's double the difference between Vancouver. Like we said before, Vancouver has about a 20-degree difference from its coldest cold average to its highest high average, whereas Lethbridge has a 40-degree difference. Now, why is that? Well, because on really hot days, the ocean will absorb a lot of that heat. Okay, and because water has such a high specific heat capacity, meaning that it takes a lot of energy to make water change temperature, to break apart those bonds, to separate those water molecules, the ocean can absorb a lot of heat without changing, and that keeps the land temperature more moderate. Okay. On the other hand, when cold air moves in, um, the ocean stores a lot of heat, and it can dump that heat into the air, right, moderating the cold air and keeping it relatively warm. Now, some of you might be asking, well, what about Cuba? What about Mexico? Why is it plus 35 there? Well, if you've ever been inland Mexico, if you've ever taken a trip down there and you're by the ocean, it might be plus 30. If you went inland, it would be like plus 40, plus 45, right? So again, that those are equatorial regions. We're talking about northern regions here. So of course it's going to be warmer, but if it wasn't for that ocean, it would be really, really, really hot, right? Not that plus 30 isn't really hot. As I'm taping this right now, it's like minus 15 outside. So I'd take some of that warm temperatures right now. Okay, so water, because of its specific heat capacity, can absorb a lot of energy without changing state and without changing temperature very much. And then when it's cooler, then that water can release that energy and moderate the temperatures. Okay, so Lethbridge is a case study of a city that is not next to the water, and you can see there's a huge discrepancy. Whereas Vancouver, it's the same latitude. Okay, it's southern Canada. but there's much less of a disparity between lowest lows and highest highs. So we're going to use specific heat capacity to calculate how much energy it takes to change, certain substances' temperatures. Okay, and energy is measured in a quantity known as joules. Okay, so distance is measured in meters, mass is measured in grams, all that kind of stuff. While energy is measured in joules. Now, you guys might be familiar with another form of energy measurement called a calorie. Okay, just like feet and inches are what are called imperial measurements, they're used in the United States. Okay, joules is the metric version of calories. So it's just how much energy is being put into a substance or taken out of a substance. Okay, so joules is energy. Now, the variable for energy, especially thermal energy, is Q. Okay, so Q is a variable that we will be using in our calculations around specific heat capacity. Okay, so Q can be calculated using a formula. Okay, and we use this to see how much energy is being put into a substance and seeing what effect that energy has on temperature. Okay, so what the amount of energy that's put into a substance affecting its temperature is affected by how much of that substance we have, so the mass, and it's measured in grams. Okay, the change in temperature. Okay, so we need to know how much the substance changes in temperature to know how much energy was either put in or taken out. This is measured in degrees Celsius. Okay, and how easily does the temperature change? So water doesn't change temperature very easily. Okay, something like I don't know, iron changes temperature pretty easily. So that's what's known as its specific heat capacity, and each substance has a particular specific heat capacity. So this is what is known as a constant. Okay, this is a constant. So it doesn't change. This is not a U, that's an N. Constant. This doesn't change. Um, every substance has its own specific heat capacity that's been figured out by scientists. And you will either be asked to figure that out given certain data, or you'll be given that, for particular substances. So the formula we use to determine how much energy is needed to change a substance's temperature is Q. So again, Q is the quantity of thermal energy, okay, equals mc delta T, okay? So Q is the quantity of thermal energy. It's measured in joules. Okay, M is the mass of a substance. Now we're familiar with M from our mass and molar mass and number of moles formula. Okay, it's always measured in grams. So if you are ever given kilograms or milligrams, you have to convert it to grams. Okay, and then C is the specific heat capacity of a substance, and it is joules per gram degree Celsius. Okay, and again, each substance has a specific heat capacity that's been calculated. And if you're ever asked to calculate Q, you'll be given the C for the particular substance. Okay, and like I said, it's a constant. And then delta T is the change in temperature. So remember, delta, that's delta. Delta is a Greek letter, and we use it in science to mean change in. Okay, so delta T is a change in temperature, and it's measured in degrees Celsius. Now, how do we figure that out? We take the temperature final and we minus the temperature initial. Okay, that's how we get delta T. So you can expand delta T into TF minus TI. Okay, so let's say a substance starts at 0 degrees and it ends up at 50 degrees. What would the change in temperature be? Well, 50 degrees would be my final temperature, 0 degrees would be my initial temperature, and delta T would equal a 50-degree change. temperature. Okay, so delta, and you'll see this in physics too, delta anything is a change in, and it's final minus initial. So in this case, temperature final minus temperature initial. Okay, so water specific heat capacity, and this is something you guys will end up memorizing. You'll know this off by heart. Water specific heat capacity is 4.19 joules per gram per times degree Celsius. So what this means is if I have 1 gram of water, okay, so I have 1 gram of water and I raise it 1 degree Celsius. So I raise it from 5 degrees to 6 degrees. Okay, 1 gram of water, 5 degrees to 6 degrees. It took 4.19 joules of energy to do that. Okay, so again, joules is a measurement of energy. How do we change the temperature of a subject or of an object? We get the particles in that object to move faster, right? That's called kinetic energy. We need those particles to move faster, and that's how temperature goes up. So how do we get those particles to move faster? We have to add energy into it, okay? And that's in the form of joules. How much energy do we add into it? That's kind of what we're going to figure out. But if you had 1 gram of water and you wanted to raise it 1 degree Celsius, you would have to put in 4.19 joules of energy in order to get those particles moving quicker. Okay, now this number 4.19, I know it doesn't mean anything to you. I've been telling you that water has a high specific heat capacity. So what that means, it takes relatively quite a bit of energy to raise a gram of water 1 degree. Okay, now how much do other substances require? Well, aluminum, for example, to get a gram of aluminum to move up 1 degree, it would take 0.9 joules. Okay, that's like 5 times less energy to get aluminum to move up a degree rather than water. Okay, copper. Look, copper is very low, right? It doesn't require much energy at all in order to get a gram of copper to move up 1 degree. 0.38 joules. Right? Again, remember, water is 4.19 joules. That's a lot of energy. Lead, even less, 0.130 joules per gram degree Celsius. So it requires a tenth of a joule of energy to get a gram of lead to move up 1 degree Celsius. Whereas with water, it takes 4 joules of energy. Okay, so what this all means is that water can absorb a lot of energy without changing temperature compared to other substances. Now, I'm sure there are substances that have higher specific heat capacities, but water has one of the highest. So how are we going to use this? How are you guys going to use this? Well, what I'm going to do is I'm going to give you word formulas, okay? And I'm going to ask you guys to figure out, various variables from those examples, okay? Now, what I taught you in the last lesson about the mole applies to this stuff. So these questions are going to be worth 3 marks, okay? So these questions are out of 3. Now, if you'll remember, this is a lot easier if you guys were in front of me, but imagine you're sitting in class and I'm asking you a question. Okay, can anybody tell me where the 3 marks come from in a question like this? Okay, think about it for a second. Remember back to joules. Well, we get 1 mark for listing the variables. Okay, so you're going to list the variables. We get another mark for our formula. And then our third mark comes from our answer. And to get full marks, we have to have the correct amount of sig digs, significant digits, and we have to have the correct geez, I'm losing it here, guys. Sorry. We have to have the correct unit. Okay. So our answer has to have the correct significant digits and the correct unit to get full marks. All right, so let's take a look at what they're telling me here. So they're telling me that I have 50 grams of water. Okay, so that's my mass. Now remember, mass always has to be in grams, so we're okay here. Okay, and it's telling me that the water temperature started at 25 degrees and it was heated to 50. So my change in temperature, remember, is my temperature final, which is 50.0 degrees Celsius, minus my initial temperature, my beginning temperature, which was 25 degrees Celsius. So my change in temperature was 25.0 degrees Celsius. Now remember, make sure you have that zero there. That's going to come into play later. Okay. Now, C is my specific heat capacity, and this is water. Sometimes they won't tell you explicitly in the question, but we know that water specific heat capacity is 4.19 joules per gram degree Celsius. Okay, and what they're asking for is to determine the value of Q. How much energy, okay, went into this water to make it go up 25 degrees. Okay, so the base formula is Q is equal to MC delta T. Okay, I don't have to manipulate this formula because it's asking for Q. So Q is equal to 50.0 grams. Okay, I like to put it in brackets just to separate everything out, times C, which is 4.19 joules per gram degree Celsius. Okay, and delta T was 25.0 degrees Celsius. That was my change in temperature. Okay, so Q is equal to, so I just need to take my calculator and plug these numbers in. Okay, remember, keep the numbers in your calculator right to the end, and then we round after. So 50 times 4.19 times 25.0 gives me 5,237.5 joules. Okay, now I can't use that as an answer. Oh, I could, but I would lose marks. Okay, what do I need to do to this? Well, I need to figure out the correct sig digs, right? So my mass here has 3 significant digits. My temperature change has 3 significant digits, and my delta or my specific heat capacity has 3 significant digits. So I would have to convert this into 3 significant digits. Now, the easiest way to do that is to put it into scientific notation. So it becomes 5.24, I'm rounding here, right? 5.24 times 10 to the 1, 2, 3 times 10 to the 3 joules. Okay, so I listed my variables. 1, my formula that I used. 2, my answer with the correct sig digs and the correct units. Okay. Now, example 2. How much will the temperature change if 41.9 kilojoules of thermal energy is added to 1 kilogram of water? All right, so let's list my variables. What are they telling me here? Okay, so joules, kilojoules in this case. Okay, that's energy, that's Q. Now, they're telling me that it's 41.9 kilojoules. Okay, I can't leave it like this because Q is measured in joules. So I have to convert this. What does the prefix kilo means? It means that it's 1,000, right? So it's like a kilometer. If I have 1 kilometer, how many meters do I have? Because meters is the base unit for distance, right? I have 1,000 meters. So if I have 41.9 kilojoules, I have to multiply this by 1,000 in order to get joules. Okay, and this is 41,900 joules. Okay, so I converted kilojoules to joules by multiplying by 1,000. Now they also give me mass. Okay, and they tell me that my mass is 1,000 kilograms. Again, 1 kilogram. I'm getting ahead of myself here. So in order to convert this to the base unit, which is grams, that's what mass is, Again, kilo is the prefix for 1,000, so I have to multiply by 1,000. So I get 1,000 grams. Okay. Now, what they're asking for is the change in temperature. That's the unknown. But you might also say, well, what about C? They're not telling me what C is. Well, we know what C is for water. Okay, it never changes. Specific heat capacity of water is always 4.19 joules per gram degree Celsius. Okay, so we always know that. Now, so here we go, 1 mark. Okay, next we have to look at my formula. Q equals mc delta T. I cannot use the formula this way because what I need to do is I need to solve for delta T. So how do I get delta T all by itself? Well, I divide by mass and I divide by specific heat capacity, okay, because I'm multiplying. That'll get rid of those there, and I have to do the same thing here, okay? So delta T is equal to Q divided by MC. Okay, so next I substitute in my values. 41,900 joules divided by mass of 1,000 grams times 4.19 joules per gram degree Celsius. Okay, now remember your bed mass. So I have to multiply the bottom two numbers first. So this would equal 41,900 divided by 4,190. Okay, so I think this is going to work out pretty nice. So what this tells me is that by adding this much energy into 1,000 grams of water, the temperature change, so delta T, would be 10 degrees Celsius. Now, if you gave me this as an answer, would you get full marks? So let's go back and look at my original data. 3 significant digits, 3 significant digits, 3 significant digits. So in order to get full marks, I would have to put 10.0 degrees Celsius. Okay, so by putting in 41,900 joules of energy, I only raised that kilogram of water by 10 degrees Celsius. Okay, so mark there, mark here for the formula, and then mark here for the correct answer with the correct sig digs and the correct units. Okay. Now here are 3 practice problems. I want you guys to take a second and try these in your note package. Okay, you can pause the video right here, go give these a shot, and I will do them, and then I'll assign some homework. Okay, so pause the video right here, go and look at those questions. Okay, come back in a few minutes. All right, so what you guys need to get into the habit of is you need to get into the habit of arranging stuff properly, okay? Again, this is going to serve you very well in Chem 20. It's going to serve you very well when we get into the physics unit, okay? It's organization. Everything has to do with organization, okay? These questions are always done the same way, and as long as you're organized and you do it in a nice, disciplined, step-by-step, you'll always be fine. Okay, so the first thing you want to do is list your variables. Okay, mass, 200 grams. And we're good there, right? We don't have to change it. It's not in kilograms, it's not in milligrams, it's in grams. Change in temperature. Okay, the change in temperature is it finishes off at 22 degrees Celsius. That's my final temperature. And it started off at 4 degrees Celsius. So it was warmed up. We had to put energy in to warm it up. Okay. C, specific heat capacity for water, is always 4.19 joules per gram degree Celsius. And what they're looking for here is Q. Okay, they want to know the amount of thermal energy absorbed. So how much heat, how much energy, that's heat is just energy, how much energy did I have to put into this 200 grams of water to raise it 18 degrees? Okay, 18.0 degrees Celsius. All right, so put your formula, MC delta T. Okay, substitute in your numbers from your variables. 200 grams, 4.19 joules per gram degree Celsius, and the temperature changed by 18.0 degrees Celsius. Okay, so Q is equal to, okay, it's just take the numbers and multiply them together, 15,084 joules. That's how much energy it took to raise this 200 grams of water 18 degrees Celsius. Now, this is not my answer, right? Because it has the wrong amount of significant digits. So I'm going to change it to 3 significant digits. I'm going to do this by moving the decimal place 1, 2, 3, 4 places. So I get 1.51, right? I'm rounding here, times 10 to the 4th joules. All right, so now I have 3 significant digits and I have the correct units. So 1 mark, 1 mark, 1 mark. Okay? Now, determine the quantity of energy required to warm a 1 kilogram block of ice from minus 15 degrees Celsius to 0 degrees Celsius. The theoretical specific heat capacity of ice is 2.00 joules per gram degree Celsius. So we're not talking about liquid water anymore here. We're talking about ice. Ice has a lower specific heat capacity than liquid water. Okay, what that means is if you have ice and you want to warm it up, right? Ice is not always at 0 degrees. If you have a block of ice sitting outside and it's minus 35, that block of ice is minus 35 degrees, right? So not all ice is 0. 0 is just the freezing and melting point of water. So, if we had a block of ice that's at minus 15 degrees and it's going and is warming up to 0 degrees, that's going to take some energy to do that. Okay, and the specific heat capacity of ice, just like water vapor, is different than liquid water, and it's actually a little bit lower. Okay, so again, we're going to go in and do the same thing. We have a 1 kilogram block of ice. Now again, I can't use kilograms, so I have to convert it to grams. All right, my delta T is final temperature minus initial temperature. So the final temperature is 0.0 degrees Celsius. Okay, the initial temperature minus 15.0 degrees Celsius. Whenever we minus a minus, that's like adding a plus, right? So my change in temperature was 15.0 degrees Celsius. All right, and the specific heat capacity of ice, it's not liquid water, it's solid water, is 2.00 joules per gram degree Celsius. All right, and what they're looking for here is they're looking for the quantity of energy required. So what they're looking for is Q. Okay, so again, I don't have to manipulate this formula. It's already the way that I want it to be. I just have to plug in the numbers. The trick to this question was just making sure that my kilograms was turned into grams and that I'm using the specific heat capacity of ice, which is 2.00 joules per gram degree Celsius. Okay, and then my temperature change was a positive 15.0 degrees Celsius. All right, so Q in this case is equal to 1,000 times 2.00 times 15.0. Okay, we get a Q of 30,000 joules. All right, so if I go back and I take a look at my significant digits, I have 3 here, I have 3 here, there's a decimal there, and I have 3 here. So again, I need to convert this into 3 significant digits, and I'm going to do that by converting to scientific notation. So my decimal place moves 4 places to the left, 3.00 times 10 to the 4th joules. Okay, 1, 2, 3. Okay, the last question here, we're dealing with iron. Okay, so iron is not water. It's not going to have the same specific heat capacity. In fact, we know that it's much lower, right? It takes less energy to heat up iron than it does water. So this one's a little bit different here because they're telling us how much energy they used. So they're giving us Q. 21.6 joules of energy was put into a 2.0 gram piece of iron. Okay, now the delta T, they tell us in here that it changed by 24.0 degrees Celsius. And what they want to know is what's the experimental value from this experiment? What is C? Okay, what's the specific heat capacity? So Q is equal to MC delta T. We want C all by itself. So what we need to do is we need to divide by M, get rid of M. We need to divide by delta T to get rid of delta T. What we do on one side, we have to do to the other. So C is equal to Q divided by M delta T. Okay, C is equal to 21.6 joules divided by 2.0 grams times 24.0 degrees Celsius. So C is equal to 0.45 joules per gram degrees Celsius. Okay, so the experimental specific heat capacity. Now, can I leave it like this? Here I have 3 significant digits. Here I have 3 significant digits. Here I only have 2. So I'm okay here with 2 significant digits, right? So my answer would be good here. So this is a very low specific heat capacity when we compare it to water. And we actually see that when we look at the theoretical specific heat capacity for iron. All right, so every question you're going to get with this stuff is basically going to be the same. We have to look at what substance we're using because they're going to have different specific heat capacities. We may have to manipulate the formula, but otherwise, if we just follow these 3 steps and keep ourselves organized, it's fairly easy. Okay, so what I would like you guys to do now is on page 75 of your note package, there are 8 questions. Please take a look at those 8 questions and work through them. If you have any questions on the homework, like usual, please email me, or I'm going to start to try and do once a week. I'm going to try and do these Microsoft Team live meetings, and you can ask me some questions then as well. Okay, but if you have any pressing questions, please, by all means, don't hesitate to email me. Okay, good luck, work on that homework, and we will talk soon.